All right, so in this case, I want to predict the result of an alpha decay of radium, not radon, but radium-226. So I want to find out where radium is. Radium is 88. So radium is number 88. Its atomic chemical is, or symbol, sorry, is Ra, and this is 226. Okay? It's going to undergo alpha decay. So it's going to lose an alpha particle. So it's going to lose a 4-2. You write helium here, you can write alpha. I'm going to write an alpha because I like that better. And it's going to produce another particle, which will be excited, and then it will release gamma as well. So I'm put a little gamma there on the side. So I'm not going to write the excited particle with the little asterisks. I'm just going to write the unexcited one, assuming that's already de-excited as still. So let's figure out what it does. So here, the bottom number's got to add up to 88. So the bottom number of this one has to be 86, because 86 plus 2 is 88. So what is 86? Oh, it's radon. So Rn. The top number's got to add up to 226. So this is going to be 222. So radon 222. Hey, that's the number it has there. That's pretty cool. And there you go. Not too bad. So this is my daughter particle here. So my daughter particle is going to be radon 222. Oh, I don't know what I'm spelling there. There you go. Cool. A few things we'll talk about later on as well about the health effects of radiation. I don't know, maybe I'll skip that part. Not the most important. It's very important if you're dealing with radiation all the time. But alpha decay, it's apparently poor penetrating power because two factors. It's usually traveling slower because it's more massive, and it's larger in size. So it's more likely they're going to hit something on the way. So it could be stopped by simple paper or cloth suit, right? Or paper suit as well, right? So you see those guys in those big contamination suits and stuff. That's pretty thin material. It's not good stopping all radiation. It's just stopping the alpha particles from hitting it. Okay? It's dangerous if it gets inside your body, because if you ingest alpha radiation, it gets inside you, it's less likely that it will leave your body without hitting anything. So it's going to hit your insides and bounce around and what we call ionize your body. Remember, we talked about this in the previous chapter. Previous chapter? Yeah, actually just the previous week when I talked about the Bohr model. If I ionize, if I have enough energy to knock an electron off your atom, you ionize it. If you ionize an atom, then it starts bonding and doing weird things within your body. It causes cancer, breaks down your DNA and a bunch of other things too. So we don't want ionization to happen within your body. So when we talk about radiation, because radiation is happening all the time, like light is radiation from your walls, from the wires in your walls, right? It's all radiation, but the ionizing radiation is the dangerous stuff. So we don't want that. A different type of particle, or a different type of decay, which we kind of mentioned already, is the beta decay. Now, beta decay, denoted by the B, is the same as an electron. It's the exact same as electrons. So when I talk about beta decay, it's very specifically beta negative decay. If I don't put the word negative after it, we assume it to be a negative. That's if I just say beta decay. Let's assume it's negative. Now, beta decay is a very complex process if you think about what's actually happening. There's a little picture down here, but what's actually happening here. But it's just the emission of a high-speed electron. Much more penetrating power, much smaller, much faster, can actually pass through much more expansive parts of air and water before it actually hits something and it actually causes damage. So if you ingest it, most likely it'll leave your body before it hits anything, but it can pass through your clothing, probably enter into your body and hit something more likely than alpha decay. Okay. There are two types of beta decay, beta positive and beta negative. Right? Beta negative is what we're going to talk about first here. Beta negative is this one, and beta positive is this one. Looks the same, but I have a little positive on the bottom. Now, if this is an electron, then what is this one? Well, this is what we call a positron. It's an electron that's positively charged. So it's an antimatter particle that actually has pretty much the exact same properties as an electron, same mass, same, just same mass. Has a different spin. There's some quantum properties that are different. Gives it an opposite charge. So rather than being negative 1.6 times 10 to the negative 19, it's positive 1.6 times 10 to the negative 19. Now, if matter and antimatter collide, they undergo what we call annihilation. They just disappear, become pure energy. We'll talk about that the very last week of this chapter. Okay? So one thing that also is emitted at the same time through beta negative, so this is still we're at negative right now. We'll worry about beta positive in a bit, is that there's another neutral particle. Neutral is very key. Very small, high speed antineutrino. It is antimatter, right? So an electron is regular matter. It produces antimatter. So this neutrino is denoted by the letter V, and because it's anti, we put a line on the top. So whenever you see like a little line on the top, it represents antimatter. So it's this little V. So to complete this down here, what I'm going to do is I'm going to add that neutrino on here. Also, I'm going to add gamma. Now, the same explanation why the gamma pops up, because it changes. It goes from 6 to 7, kind of like before it lost 2 protons. The energy shells have to change to accommodate for that. When my energy shells change, all the electrons have to move to the new position, and out comes a gamma particle as well. So there is an excited state, so this gamma is also there as well. Okay, so what's actually happening here is I have 6 protons, and all of a sudden I gain a proton. But you notice on the top here, my nucleon count didn't increase. Like I gained a proton, but wouldn't that mean my nucleon count has to increase as well because a proton is a nucleon? Well, what's actually happening is this. A neutron, one of the nucleons in here, becomes a proton. So the nucleon count stays the same. A proton's a nucleon, neutron is a nucleon. So when one changes to another, the nucleon count stays the same. But because a neutron changes to a proton, my proton count has to increase as well. So my proton count increases. You notice that it shoots off an electron. A proton is positive, and this guy down here is neutral. There's still a conservation of charge here. That's very important. This over here is neutral. It's a neutron, which makes sense, right? So its charge is 0. So over here, everything's got to add up to 0 as well. All right, and this charge, this guy down here, is also 0. So this one here is plus 1e, and this one's negative 1e. So that still balances out. So charge is balancing, nucleon count balances, okay? And yeah, so everything kind of works out, but mass is going to change because the proton and neutron's masses are different. Now, another key thing about this is that these electrons and these protons and this antineutrino are not inside that neutron. It's not like all of a sudden it just like splits apart into these 3 pieces. What happens is there's an intermediate step where the neutron blinks out of existence. A particle, what we call a virtual particle, which in this case we call a boson. We're going to call it a W boson. All right. That boson then decays. So this boson is a massless particle. It's massless, it's virtueless. Or is it massless? I can't remember now. Maybe it's not massless. But it's high energy. The neutron disappears, becomes this boson. The boson then decays, disappears, and it decays into these 3 pieces. I think the W plus or minus W is a Z. Is it a W boson? We'll double check. I know it's a boson. I just can't remember if it's a W boson. That's not important. It's just that these three particles are not inside the neutron. The neutron disappears, becomes energy, it becomes a new particle, and then it decays into three particles. Okay, we'll talk about this later on. It's very unlikely this happens. A floating neutron. Well, let's see. I can't remember which one's which. One of these is more stable than the other. One will decay into the other more likely. Anyway, in this case, it's a W naught boson. If it's a neutral one, there's a W positive one as well. Okay. So what is the element in the decay of thorium in this process then? So let's say thorium. Is this right? I have to double check that. I may have mistaken one of these before. So carbon becomes nitrogen, everything adds up there. Yeah. Okay, I fixed this one. Good. What element will the decay of thorium produce? Now, the problem is that we don't know what thorium isotope we're talking about, so let's just assume that we're talking about thorium-230 or something. Just makes it a little bit easier to just do that number on the top there. Thorium is always 90, okay? It's going to undergo beta negative. Let's assume it's doing beta negative here, right? So it's going to undergo this. Now, the bottom number's got to add up here. Okay, so if my bottom numbers had to add up, this has got to be 91 to make sure this adds up. The top number's got to add up. So this is going to be 230 because that's a 0. Now here, what's 91? Does my hair disappear when I look away? Yeah, it does. 91 is protactinium. So that's PA, so it's right beside that one. Other particles we had to deal with, so it's antineutrino and the gamma radiation. Now, antineutrino, by definition, neutrino, it's like a neutron, neutral. It is 0 charge, so there's a 0 here. And it's so small that you cannot consider it to be a nucleon, so it's a 0 on the top. It has mass, but it's so small we consider it to be 0 on the top. It's just like here. It's so small, it's an electron. Compared to a nucleon, an electron is so small, that's why we say it has 0 on the top. What's the nuclear reaction that represents the beta decay of actinium? Actinium, let's go here. I spelled it wrong. Actinium-227. So this should be spelled differently. Actinium. Okay. So actinium is AC. It is 89. It's right beside thorium there, which gives away what it's going to turn into because it's going to release a beta particle, an antineutrino, a little bit of gamma, and then this bigger daughter particle. So this is going to be 90, which we already know is thorium, and this is thorium-227 this time. Cool. How much energy do you expect to be released from the decay of thorium-234 in this process? So first of all, because what we're going to do for this is very similar to what we did before with mass defect. We've got to find the mass of the products, the mass of the reactants, compare the two sides. If we lose mass, we gain energy, and then we can find out what that is. So first of all, let's find out what thorium-234 turns into through this decay process. Now, there's one thing we keep on missing here in terms of electrons and charge of the particle afterwards. I'll show you that later on. Why is that? What I'm talking about. Becomes protactinium again. Got to add up to 90 on the bottom, adds up to 234 on the top. Got the extremely small neutrino. We got the massless gamma particle. Now, the one thing that I'm missing here is how many electrons are there to start off with, because I'm gaining an electron. Electron just pops into existence. So we start off with 90 electrons. So this has 90 electrons as well. 90 electrons, but it doesn't say 90, it says 91 here. It has 90 electrons because this guy had 90 to start off with. 90 electrons because he's an atom. Electrons, 90 protons. This guy over here has 91 protons, but 90 electrons because he didn't gain or lose electrons. That electron just popped out of nowhere. It's just kind of into existence. So technically, this is a positively charged ion of protactinium. The fun thing about this is that this new electron that popped into existence, now I have 91 electrons. So all together, this is neutral, right? And over here, this is neutral. Okay? So neutral, neutral, everything, conservation charge does work out here. Now, the idea that this is neutral is that when I talk about the mass of protactinium, let me just find a sheet for you, just one second. Okay, so I'm usually going to give this file to you. I'll share with you so you can see it. If I can find it now, where did it go? I just brought it up to my other slide here. Oh, here it is. Here. So this file has, it's part of one of the assignments, assignment number 2. It's attached to the bottom of it. There's a bunch of information about all the atomic masses using atomic mass units of all the different elements. So these numbers are for atoms. They include the electron masses and they include the proton masses and the neutron masses. So all of that together. So these are not ion masses. So that's very important for one of these kind of questions, because if I didn't have this beta particle here, this would not be an atom anymore because it doesn't have the same number of protons and electrons. So I couldn't use these numbers as is. I'd have to kind of subtract out an electron. There's an electron number somewhere on the sheet, I think, down here. I'd have to subtract this number out because it has one less of those numbers. It's a really small number, so it doesn't really change too much, but it does change it. So you do have to kind of watch how precise you're going to do your answers. So these are all atom numbers. Okay, so neutron or neutrino is so small we don't even count it, and massless gamma we don't even count it. So when I'm looking at this, I want to know what the masses of these two sides are. So the mass of the thorium-234, that's on the sheet here, mass of 234, 234, blah, blah, blah. I'm just going to write it down. I'll put it on my other screen here. So the mass on my reactant side, so my mass of my reactants, the reactants is the left-hand side here, is 234.03 or 043061060. I'm writing down the right numbers. I'm just not saying them. Atomic mass units, okay? And then the mass of my products would be the mass of this ion plus this one electron, which together makes an atom, because now it's neutral. So I could just look at the protactinium number, the atom number here. So I'm not going to deal with adding an electron here because together they make an atom. So I'm just going to use the atom number. 308. So that's why these numbers have to be super precise, because they're relatively the same. But you notice my product mass is less. And then you can add the neutrino and the that's it, just add the neutrino, but the neutrino is too small to care for. Okay, but the mass is different. So there is a change in mass or a defect. Now you can't say there's a binding energy, but there is a defect mass here. So there is a defect. So I'm going to go mass of the products minus the mass of my reactants, and or the other way around, reactants minus products. That's a good idea. Let's do it that way. So I get a positive number. Actually, you put negative, makes more sense because you're losing that mass. Products minus reactants. Okay. So the number ends up being, let's see if we can go here, my calculator. Boop. What do we have here? 601 minus 308. So we get, just because I know all these other numbers are going to be canceling out. So the 293 atomic mass units. Cool. That's how much it changes by. So how much energy is being released then? Okay, so what I'm going to do here is I'm going to change this into kilograms by multiplying by its atomic mass unit conversion factor, the 1.66 times 10 to the negative 27 kilograms per atomic mass unit. So those cancel each other out. I'm left with kilograms here. Now the reason I'm doing kilograms is because the formula that I'm going to use, that we used in the previous lessons, E is equal to mc squared, this has to be in kilograms, right? I'm going to get joules out. Got to be in kilograms. 1.66 e to the negative 27. So I'm going to get 4.8638 times 10 to the negative 31 kilograms. So it's quite a small amount of mass there. Okay, so I'm going to put that number in here. Times it by c squared, which I'm not going to bother writing out. Just the speed of light squared. So I'm going to get 4.37742. I'm going to write all my my decimals there. Deal with the sig-digs in a bit. Times 10 to the negative 14 joules. Because we're talking about atomic physics, it's nice to change this into electron volts. So in order to do that, you can divide by 1.6 times 10 to the negative 19 electron. Oh yeah, you're dividing by joules. So joules per electron volt. So divided by that. Okay, so I'm just going to do that quickly. Divide by that number, and I get 273,000, so 74 kilo electron volts. Because remember that's 273,588 electron volts. So I'm going to change the prefix by moving over 3 spaces and I get kilo. I'm not going to go mega because that would give me a decimal number, like 0.274 mega electron volts. It's not bad, but this is a much nicer number. Cool. Now, where did that energy go? So is that energy going, well, it's going somewhere. It's got to maybe move these particles away from each other. So that's going to be kinetic energy. That's pretty much it. Yeah, nothing else really. These photons, remember I said, are produced some other way through the moving of electrons and stuff. The other type of radiation, which is beta positive, I was going to write them positive like a cat. Okay, it's positive. Beta positive radiation involves the emission of a positron, which has a charge of positive 1, same mass of electrons, so that's going to be important for later on too. And sometimes you can write it as E positive, sometimes you can write it with a little positive 1, 0, and E there. But all those are kind of interchangeable to each other. Now, this is an anti-electron. It says think of it as an anti-electron. It is an anti-electron. Same mass, but opposite charge. And that's usually how antimatter is. It usually has the same mass, but has an opposite charge. Now, if it's like a neutron, like an anti-neutron, how does it have opposite charge? Well, it's something about its spin. There's another quantum property which we don't delve into. It's like I think you call it the spin. It depends on which way it's going, left or right. It tells you if it's anti or not. I just want to make sure this is the proper one. Now this one is broken. So fluorine becomes 8. 8 here is oxygen. I just want to make sure I fix that before we go any further. It's not nitrogen. Remember, nitrogen was 7 of one of our previous examples. But everything follows the same path, right? So all the top numbers got to add up. All the bottom numbers have got to add up. Now, this will also release a regular neutrino, not an anti-neutrino like the previous one, but a regular neutrino. So this one doesn't have a line on the top. Or sorry, there's another way to write this too. an electron with a line on the top. Yeah, anything with a line means anti. But we usually write it with a little E positive, represent that, but still antimatter. So this here is antimatter. I don't know what I'm spelling. And this is regular matter. They come in pairs like that. If you're going to create matter, you usually create antimatter to come with it. And of course, your typical gamma, because they are excited because these energy shells are different. One has the energy shells of a 9-proton molecule, or sorry, atom, and then now it has an energy shells of an 8. So the electron's got to move around. Cool. Okay, I think this video is way too long. So we will stop this video here and we'll talk on the next part, part 3, write about these chemical reactions. And I'll see you then. Bye.